When a patient is undergoing open heart surgery, the heart-lung machine is their lifeline. And the absolute core of that machine is the oxygenator, basically an artificial lung. But here's the thing, not all of them are created equal. So how do these different designs actually perform under pressure? Well, we're going to dive in and find out.
So here's our roadmap. We'll start with the basics of the artificial lung. Then we'll jump into a head-to-head comparison of 3 common devices. We'll look at the pressure drop results, which are pretty eye-opening. After that, we'll talk about what this means for stress on the blood. And finally, wrap up with the clinical implications and the big questions that remain. All right, first up, the artificial lung. Now, think about this for a second. Your own lungs have a surface area of about 100 square meters to get oxygen into your blood. An oxygenator has to do that exact same critical job in a space that's a tiny fraction of that size. And as you can imagine, that creates some serious challenges, especially when it comes to pressure. The one number we really need to focus on is pressure drop, or delta P. The easiest way to think about it is this. It's a measure of how hard the machine has to push blood through the device. So a higher pressure drop means there's more resistance, and more resistance can mean more mechanical stress on the delicate blood cells as they pass through. So, to see how this all plays out in the real world, we're going to dig into a prospective observational study from Heidelberg University Hospital. What's cool about this is that the researchers tracked the performance of 3 different commercial oxygenators while they were being used in actual cardiac surgeries. The study pitted 3 heavyweights in the field against each other: the Medtronic Affinity Fusion, the Eurosets A.L. 1+, and the LivaNova Inspire 8F. To make it a fair fight, they took 60 patients and split them into 3 equal groups, with 20 patients for each device. This lets us see a direct, real-world comparison. And they were not messing around with the data collection. Just look at this timeline. They weren't just taking one measurement. They took readings at multiple, very specific points throughout the entire surgery, from before bypass, during the critical aortic clamping phase, and all the way to reperfusion. This makes the data super robust because it captures performance across the whole procedure. Okay, so what did all this careful measurement actually show? Let's get right to the results, because this is where a really clear and frankly dramatic pattern started to show up. The bottom line was, well, it wasn't subtle. Across all the measurements, one of these 3 devices consistently put up way more resistance to blood flow. It had a much, much higher pressure drop than the other 2. And this chart, wow, it just lays it all out there. If you look at the peak pressure drop during that critical aortic clamping period, you can see the Medtronic and Eurosets devices are pretty close, right? Around 116 and 123 millimeters of mercury. But then you look over at the LivaNova Inspire 8F, and it's in a whole other league, hitting a peak of 168. Let me put a big, bold number on that for you. When the researchers averaged everything out, the pressure drop across the Inspire 8F was a whopping 46% higher than the Medtronic Affinity Fusion. In the world of hemodynamics, that is a massive difference. So a higher number on a chart is one thing, but what does it actually mean for the patient's blood? This is where we connect the dots between that pressure reading and the very real potential for blood trauma. It's a simple question, right? But the answer is absolutely critical for understanding why these findings are so important. So why do we care so much about a higher pressure drop? It's basically a chain reaction. A high pressure drop tells you there's high resistance. To get past that resistance, the blood gets forced through the oxygenator's tiny fibers with more, well, force. That creates what's called shear stress, and that physical stress can literally damage or even destroy red blood cells. That's a process we call hemolysis. And hey, don't just take my word for it. The authors of the study spelled it out perfectly. They said that seeing a higher pressure drop directly correlates with a greater mechanical load imposed on the blood components. It's a direct relationship. Now, the crucial question. Could this have been because of the patients or something unique about the surgeries? Nope. The researchers checked for that. They normalized the data for blood flow, and the huge difference was still there. That points the finger directly at one thing: the internal design and architecture of the oxygenators themselves. So that brings us to the final and, you could say, the most important part of all this. What do these findings actually mean for perfusionists and doctors in their daily practice, and what big questions are we left with? So here's the breakdown. On one hand, the study makes it crystal clear. There are major device-specific differences in performance. The LivaNova Inspire 8F definitely produces a higher pressure drop. But, and this is a big but, the study didn't actually measure hemolysis or patient outcomes directly. So the huge question that's still on the table is, does this higher pressure actually lead to worse results for patients? So, what are the big takeaways here? Well, for one, we know that a rapidly rising pressure drop is a huge red flag for oxygenator failure. We also know this extra mechanical load could potentially set off coagulation cascades. That means the specific device a team chooses could really influence how much trauma the blood goes through. But to be 100% sure, we absolutely need more studies that connect these pressure differences directly to clinical outcomes.
And all of this leaves us with the ultimate question for everyone in this field. This study clearly shows there's a difference in performance, but it also raises an even more urgent issue that clinicians and engineers have to solve. Exactly how much of a pressure difference is too much for patient safety? That's the question we need to answer.